Okay, relating to the negative binomial distribution and collections of stacking geometric distributions on top, there's a well-known and famous class of problems in probability called coupon collecting. The idea it goes under the heading of coupon collecting, and in general, a lot of different things can be classified as coupon collecting. And what it means is, the general idea behind it is, you imagine that you have a box of coupons, and so you imagine you have a box of, let's say, n distinct coupons. There are ways to generalize this and so on, but you have n different coupons in a box, and what you do is you want to you're going to pick into the box. You're going to pick one out, and once you see it, you're going to put it back in. You're going to pick another one out, and so the question is, if I do that, so successive draws, and this time with replacement, how long will it take until every coupon is chosen at least once? So, your first choice is going to be a new coupon. You're going to put it back in the box. And then as you continue to pick, you're going to probably pick a duplicate, right? And triplicate and so on. And eventually, you're going to get to the point where you've seen all the coupons except one, right? So the next one you pull out is very likely to be one you've already seen before, and it gets harder and harder and harder to get a unique coupon. And so the question is, how long does it take to actually get that last one? And so we're going to illustrate this in the context of, let's suppose we're rolling a six-sided die. How long until each face is rolled for a six-sided die? So we're going to roll a single six-sided die. And what we want is, okay, the first roll might come up 2. And then we're going to roll again. And the next roll might come up 4. And then we're going to roll again. And maybe that roll comes up 2 again. So that's not a new, we've already seen the 2. And the next roll comes up 3. Then the next roll comes up 2 again. Then the next row comes up 3, and then we see a 5. And how long until we see every outcome at least once? 1, 2, 3, 4, 5, 6. Okay. So we're going to roll a fair die repeatedly until all 6 faces appear. And we want to let n be the random variable number of tosses required to do that. Right? So an example would be the example I just gave: 2, 4, 2, 3, 2, 3, 5, 1, 5, 1, 6. So this would be a case where n is equal to 11. So we see the 2 here, the 4 here, the 3, 5, 1, 6. Right. And that's when we've seen all 6. Okay. So it's pretty, to state the obvious, it's obviously going to take at least one roll to do this. What's the distribution of What's this distribution? Well, put some notation. So one way to do it, there's a couple of ways we can do it. One would be, when in doubt, we can just try to brute force it for all intents and purposes, or just go back to the basics. So how do we define the event? So we want to define the event that it takes us at least little n rolls. Okay, so let's say we were interested in calculating that it took us it took us more than n rolls. Of course, for n, some value n, and n is of course going to have to be bigger than or equal to 6, generally speaking. But how might we do this? Well, in order for us to have to roll at least n times, it means that one of the faces hasn't come up in n rolls. So let's define events. I'm going to define event f sub I of n is going to be defined as the event that I does not appear in the first n rolls. Okay. And so with that, I know that the probability, the event that I need more than n rolls is just the union over all of the faces, I equals 1 to 6, of these events f sub I of n. Okay. And okay, how does that help me? Well, the way that helps me at least to start is that I know that I have inclusion exclusion. So probably of a union is going to be S1 minus S2 plus S3 minus S4 plus S5 minus S6. This is by inclusion exclusion. Where S sub K, remember, is defined as the sum over all sets, index sets of size K, of the intersection for each K. Now, we could try to do this, and we could calculate, well, what's the probability? What's S1? Well, for that, we have to calculate the probability of FIN for each I. This is 5/6 to the n. Why? Well, FIN is the event that I does not appear in the first n rolls. How does I not appear in the first n rolls if something other than I appears in every one of those n rolls, the first n rolls? So, and what's the probability? It's 5/6 each time, right? Because it's 1/6 to hit the number each time. And we multiply it together. Okay, what about the twofold intersection? Well, if I'm not going to see I and I'm not going to see J, well, that's 4/6 to the n, because now I have to avoid two numbers each time. And so on and so forth. For 3, it's Fi intersect Fj intersect Fk. I have to avoid 3 numbers. And so on. And so I can calculate probability that n is bigger than n by, okay, how many different, then it comes down to, for each k, how many subsets of a given size are there? Well, in this case, there are 6 subsets of size 1 times the probability of avoiding that 1 minus 6 choose 2, 6 choose 2 subsets of size 2 times the probability of avoiding that, plus 6 choose 3 times the probability of avoiding all 3, and so on. So we could calculate that and have an explicit expression, and then from this we could derive the probability that n is equal to n as probability that n is greater than n greater than n minus 1 minus the probability that n is greater than n. Although we still don't have a very closed form formula for it, we do have a way of calculating the probabilities, which is nice. If we want to calculate expectations, so how long do we expect to have to wait to see the nth, to see all the faces, and what's the variance? Well, for that, we want to be a little more clever, because if we have to calculate probabilities based on this, it's gonna be difficult. If we have to generate a sum over all the possibilities, a weighted sum. So for the expectation, we can use a similar approach to what we've shown in the up above previously in the case of the negative binomial. Negative binomial, we were able to express the random variable as a sum of independent, identically distributed geometrics. In this case, it's not going to be independent, identically distributed. It's going to be independent, but not necessarily identically distributed. Why? Well, if we realize that we can express n as 1 plus x1 up through x5, where xi is the number of rolls needed to produce the I plus first new face. So we know that where does this 1 come from here? We know that we're going to see a new face on the first roll because we haven't seen any faces, and we're going to see something on the first roll. So then the question is, okay, how long do we have to see the second new face? That's x1, and so on and so forth. So what is the distribution of each of these xi's? Well, for xi, we're trying to see the I plus first new face. So we have to avoid the previous faces. So the probability of a success is 1 minus I over 6 in general. So x1 is geometric 5/6. x2 geometric 4/6. x5 all the way to x5 geometric 1/6, and these are independent. So this gives us a clear way to calculate expectation. Expectation of n is sum of the expectations. Let's write x sub 0 as uniquely 1. And so this ends up being equal to sum from I equals 1 to 6 of 6 over I. We can pull the 6 out. 1/6 plus 1/5, etc., all the way to 1 gives us 147 over 10. So about almost 15 rolls to see all. And the variance by independence, the variance is the sum of the variances. And we know the variance of geometric and so we can no variance to the first one, so it's just the last five, x1 through x5, x1 through x5. Okay, and so what this looks like is sum from I equals 1 to 5 of 6 times 6 minus I over I squared, which is equal to 3899 over. So that's how we can use the geometric. It's not always going to be the case that that it's IID, that they're all the same. Here we expressed a random variable as the sum of other independent random variables. That proves to be, they're not all the same distribution, but we can describe the random variable in that way, and that's a very convenient and good thing to be able to think through. That's why it's important to understand how the structures of these distributions work and how random variables can be related to one another in various ways.